Welcome to The Explainer. Today we are digging into some really cool stuff from a university cybersecurity course. We're talking about two heavy hitters in our digital world, the AI that acts like a detective, and the incredible math that works as a guardian for our secrets. So let's just jump right in. Think about this for a second. Our entire digital life really boils down to two huge challenges. First, how in the world do you spot a threat that's designed to look completely normal? And second, how do you keep a conversation private when you have to assume that someone is always listening in? So first, we're going to tackle that detection problem. You have to picture our digital world as this giant invisible battlefield. And the bad guys are getting really good at camouflage, hiding right out in the open. I mean, just think about credit card fraud. You've got millions of transactions happening every single hour. A thief isn't going to use some obvious pattern. No way. They're going to use subtle tricks, things that are constantly changing, buried in an absolute mountain of normal activity. You can't just write a simple rule like, if this, then that. It just doesn't work. It is literally finding a needle in a haystack. So what's the answer? Well, let me introduce you to our first hero of the day. Deep Learning. This is our digital detective. And the cool thing is, you don't give it a rule book. Instead, it teaches itself how to spot the bad guys, learning to recognize their complex fingerprints all on its own. And it all starts with this one tiny thing, a perceptron. The best way to think about it is like a single artificial brain cell. It takes in a bunch of signals, adds them up, and then makes a super simple decision. If the signal is strong enough, it fires. If not, it doesn't. That's it. A simple yes or no. But this is where it gets really interesting. On its own, that one little neuron is pretty smart. It can handle simple logic, no problem. It gets things like A and B or A or B. But it completely hits a wall with something that seems just a little trickier. It's called the XOR problem, which just means one or the other, but not both. And that one little twist, it's totally impossible for a single neuron to figure out. And that is exactly why we need a team. You see, when you connect thousands or even millions of these simple little neurons together in layers, you get a neural network. And that network working as a team can suddenly solve those really complex, messy problems like XOR and way beyond that a single neuron just couldn't handle. Okay, so how does this team actually learn? Well, it's pretty clever. The network makes a guess. Then it looks at the right answer and sees how wrong it was. Then, and this is the key part, it sends that error message backward through the whole network. This process, called backpropagation, basically tells each little neuron, hey, you were this much responsible for the mistake. And so they all adjust their connections just a tiny bit to get it right the next time. It learns from its mistakes over and over again. But how much do they adjust? That's controlled by something called the learning rate. And it's a real balancing act. If you set the rate too high, the network makes big, bold changes. It learns fast, but it might just jump right past the best solution. But if you set it too low, it makes tiny, careful adjustments. It's more precise, but man, it could take forever to learn anything, or it might get stuck thinking a good enough answer is the best it can do. All right, let's switch gears. We've got our detective that can find threats. Now we need to talk about how we hide our data in the first place. It's time to meet our second hero, the digital guardian. Encryption. This is all about the pure math that keeps our secrets secret. And this takes us to the absolute classic problem in cryptography. You've got Alice, and she wants to send a secret message to Bob. The problem is they both know there's an eavesdropper, we'll call her Eve, and she is listening to every single thing that goes between them. So how do they do it? How can they talk privately in public? The entire foundation of modern security rests on this one really powerful idea. It's called Kerckhoffs' principle, and it basically says this. You have to assume your enemy knows everything about how your security system works. They have the blueprints, they know the algorithm, all of it. The only thing that keeps your message safe is the one thing they don't have, your secret key. So that leads us to two main ways we lock our digital information. First, there's symmetric encryption. The best way to think of this is like a normal house key. You use the exact same key to lock the door and to unlock it. It's simple, and it's super fast. Then you have asymmetric encryption. Now this is different. It uses two keys that are mathematically linked, a public key and a private key. Think of it like a mailbox. Anyone can use the public slot to drop a letter in, but only you, with your private key, can open the box and read it. But right away, you can probably see the big problem with that first method, right? The symmetric one. If Alice and Bob need to use the same key, how does Alice get the key to Bob securely? If she just sends it to him, Eve will grab it. And if Eve gets the key, it's game over. The whole system is broken. This is the famous key distribution problem. And this is where asymmetric cryptography pulls off what honestly feels like a magic trick. With a method like the Diffie-Hellman key exchange, Alice and Bob can actually create a shared secret key right out in the open while Eve is watching. It works kind of like mixing paint. They both agree on a public color, say yellow. Then Alice adds her secret color red, and Bob adds his secret color blue. They swap their new mixtures, and then they each add their own secret color one more time. And poof, they both end up with the exact same final secret color. And Eve, who saw the whole exchange, has no way to figure out what that final color is. It's absolutely brilliant. Now, this isn't actually magic, of course. It's all built on something called hard math problems. These are things that are really, really easy for a computer to do in one direction, but are practically impossible to reverse. Like, it's super easy to multiply two massive prime numbers together, but if I give you the result, trying to figure out which two primes I started with, that could take the fastest computers we have centuries. It's like trying to unscramble an egg. So let's bring these two amazing ideas back together. What we have is a digital detective and a digital guardian, and they're locked in this constant evolving code war to keep our world secure. And that right there is pretty much our entire modern cybersecurity strategy. You've got deep learning, our detective getting smarter every single day, training itself to spot newer and sneakier attacks. And at the exact same time, you've got encryption, our guardian, building stronger and stronger mathematical locks to shield our data so that even if it gets stolen, it's just a meaningless jumble of code. But this all leads to one final, kind of scary thought I want to leave you with. We're building these incredibly powerful AIs to be our detectives, right? Well, what happens when that same unbelievable intelligence gets turned against our guardians? Could an AI eventually become so smart that it can actually solve those hard math problems? Could it learn how to unscramble the egg? That question right there is probably going to define the entire future of cybersecurity.